Okay, so looking at the derivative graph, we can see the critical numbers. So I can see that at -2, I have a local max because the derivative's changing from positive to negative. And I can see at 0, I've got a local min. That's because the derivative's changing from negative to positive. At x equal 2, it is not an extreme value, but it is a place where the derivative doesn't exist. And at 3, I see I can have a local max because the derivative is changing from positive to negative. All right, so I know when the derivative graph is above the x-axis, that's when f is increasing. And when the derivative graph is below the x-axis, that's when the function is decreasing. So I'm just going to write those intervals down. So function is increasing from -infinity to -2. From 0 to 2, and then from 2 to 3, and then the function is decreasing from -2 all the way to 2, to 0, -2 to 0, and then from 3 to infinity. All right, so when this derivative graph is increasing, that's when the second derivative is positive, and that's when the function is concave up. So the function is concave up from -infinity to -2, and then from -2 to 2. And when the derivative is decreasing, that's when the second derivative is less than 0, and that's when the function is concave down. And so that would be from 2 to 6. I guess I forgot a concave up here. Concave, it's also increasing from 6 to infinity. All right, so putting all of those pieces together, I'm going to let you do the slow bit. I'm just going to give the punchline here. So at 2, I've got a vertical tangent. So that's 2, and then I've got here, and changing concavity. Whoops, let's fix that a little bit. So it just changes concavity. It's not a vertical tangent there. It's just a changing concavity point. This is a vertical tangent. This is the point 3. And so this is the point 6 where it just changes concavity. All right. Oh, and this is the point -2. All right, so from looking at this second problem here, I see 3 critical numbers. I see x equals 3, x equals 0, and x equals 5. So I need to make a number line and check numbers between those. So 0, 3, and 5. So I'm going to check values like the derivative at -1. That gives me a negative number. And I'm going to pick a number in here like 1. The derivative at 1 gives me a positive number. Pick a number in here. Derivative at 4 is a negative number. And the derivative at 6 is a negative number. So I see the sign changing of the derivative at 0. So f of 0 must be a local minimum because the derivative changes from negative to positive. Y prime changes negative to positive, and at 5 I must have, no, I'm sorry, at 3 I must have a local maximum because the derivative changes from positive to negative. All right, so moving on to, this is the given derivative graph. So if I want to draw the second derivative, I'm looking where the slope of the tangent line is 0, so -2, and at 4, so it's decreasing before that, increasing and decreasing. So that's the second derivative graph. So looking at the first derivative, I can see the critical numbers would be x equal -4 and x equals 0. So to do the second derivative test, I look to see what the sign of the second derivative at that -4 point. So that is negative, right? -4 is back here, so I'm looking at this y value. So that means the second derivative is negative concave down, so that f of -4 must be a local max. And I'm doing the same thing at 0, that's positive, so that must mean it's concave up, so f of 0 must be a local minimum. All right, moving on to the new material. So rewriting is very helpful. So you can pull that 2 outside. And looking at this, talked about how the denominator is a good inside function. So here's your du is 7 dx. So I've got the dx. So I'm just going to multiply both sides by 1/7. So I get 2, 1 over u, and 1/7 du. So just making it a little cleaner, with pulling the constants outside, I see that I've got 2 over 7 ln of u plus c. And then at the last step, put the x's back in. 7x plus 3. You need to keep those absolute value bars on the inside of the ln. All right, I'm going to let here this u equal this e to the x. It matters which one. So, oops, du is e to the x dx. So rewriting this, thinking about this, so I have secant squared of e to the x times e to the x dx. So this e to the x dx gets taken out, and I can put a du in its place, and I get secant squared of u. So we know that that is tangent of u plus c, and I put the x's back in. So here I'm going to let u equal the inside function, cotangent of x plus 3. Du is negative cosecant squared. So I kind of have that here, so let me just rewrite this. So cotangent of x plus 3, cosecant squared of x. So this is this, except for the negative sign. So I can say negative du is cosecant squared x dx. So I can replace this with negative du, and this I'm going to replace with u to the 1/4. Take the time to pull a negative outside. Then add 1 to the exponent, u to the 5/4 times 4/5. So I get 1/5, put the x's back in, cotangent of x plus 3 to the 5/4 plus c. All right, this one here, I'm going to let u equal x squared. It's on the inside. Du is 2x dx. So rewriting this, I see x dx, I see x dx, except with a factor of 2. So I'm going to divide both sides by 2. So I get cosecant of u, cotangent of u, and then 1/2 du in for the dx. So if I pull the 1/2 outside, and as you're rewriting this, you're thinking, I know that antiderivative, that's negative cosecant. So then I put the x's back in. X squared plus c. All right, this one's a little more challenging. Here I'm going to let u equal 5 to the x. Du is 5 to the x times ln of 5. So if I rewrite this, this is my u. So I get cosecant squared of u. So I need to get this out and get the du in. So I see it over here. I know that ln of 5 is just a constant, so I can divide through by ln of 5. So I can replace 5 to the x dx with 1 over ln of 5 dx. Oops, sorry, du. 1 over ln of 5 du. So I put this instead. So I can pull that 1 over ln of 5 on the outside. Oops. And get cosecant squared of u du. And I know that that is negative cotangent of u. And then I put the x's back in. Cotangent of 5 to the x plus c. All right, last one here. You could take the time to rewrite this. E to the x plus pi times e to the x dx. The denominator is a great inside function. So du is e to the x dx. There it is. I need to take that out to get the du in. So that comes out. Du goes in its place. And then I have 1 over u. And I know that that is ln of u. And then I put the x's back in. And there we are.